Now, we just walked through a solution to an example problem around formation constants for a complex ion of copper and ammonium in a previous video. I'd like to show a different way to do the solution, or to get to the same solution. So in the last solution, we assumed that all of our copper would form our complex ion because we determined it would be the limiting reactant. With a large formation constant, that makes sense. We expect this to essentially go all the way to completion and some of it to come back to reach equilibrium. This time we're just going to assume the concentrations of our reactants given the total volume that we have, and assume that all of the copper reacts, and we see that change in concentration. But we're going to call it about, and we're going to use those final concentrations at equilibrium to predict the K value, and we're going to get the same answer. So initially, we actually really need concentration. So I have the moles that we calculated before in our problem, the 0.0003 of copper and the 0.05 moles of ammonium. Now, we knew the total volume was 0.45 liters, so I'm going to divide both of these by that 0.45 liters and get the initial concentration for the reaction. So when I calculate that for copper, I'm going to end up with an initial concentration of 0.667 times 10 to the negative fourth molar. I'm going to get a concentration of 0.11 molar for the ammonium and 0 for the complex ion. So my change here is I am going to assume just about all that copper reacts. So I'm going to call it about minus 6.667 times 10 to the negative fourth. That means my ammonium is going to be minus 4 times that concentration of 6.667 times 10 to the negative fourth. And my copper complex ion with the ammonium is going to gain that. My equilibrium concentrations then are going to be X, and that X is really saying not all of it goes, but pretty much all of it compared to the other concentrations. So we'll call this X. That's what we need to solve for. When we subtract our change from our initial amount of ammonium, we're going to get 0.108. So I guess it's 89 or 0808 molar. And then we'll have our 6.667 times 10 to the negative fourth for our complex ion. Now I'm going to plug this into my equilibrium expression. That Kf value, which is equal to 1.7 times 10 to the 13th, is going to be equal to that 6.667 times 10 to the negative fourth divided by X times 0.108. And when I solve this, my X value, which will be that concentration of copper plus 2 ion, is again, just like the longer method we just did, 2.8 times 10 to the negative 13th molar. So if this is a little more intuitive, it's definitely, I think, a little bit faster. We don't have to go through that limiting reactant step or do the before change after stoichiometry table. And we're getting the same answer.